Okay, so in the so, in this section of our course, we are looking at some tools, and in the last couple of lectures, we looked at or just a basic revision of vectors and tensors, how to use them, and we did, the algebraic equations like dot products, cross products, and then after that we did differential operations with one example of how you can do differential operations when you have curvilinear coordinates. And then I just mentioned some integral theorems which could also be of some use. So now I want to move to the next part of the course, and that relates to essentially how we can do some simulations of granular flows. There's many computational methods that are available, and I'm going to tell you about one set of methods, and that is a sort of fundamental approach where you follow the motion of every particle. So let me sort of share my screen. Let's see if I can select something. Okay. Okay. So you can see it, I suppose. Okay, so so again, the next topic, first tool that we studied was vectors and tensors, and the next thing that we want to study is numerical simulation of granular flows. This is what I want to start doing today. So the basic idea is this, that supposing we have a domain, I'm just drawing, it can be any shape of course, but supposing we have a square domain like this, and there are many particles in here, and I'm drawing them, we'll mostly be considering spherical particles. Correct? And let's suppose they're all moving with some velocities. Okay. Now what we would like to do is, we'd like to calculate the motion of every particle. So this is not something that is very complicated for you, because you have already done this. In all of physics, you keep on finding out what is the motion of a particle under gravity, and if you throw it at this angle, how will it move, and so forth. So the basic law that you have to apply to solve this problem, and that is Newton's law of motion. So suppose we have not just one particle, but let's say we have n particles in the system, and for each particle we'll have, let's say, we call each particle by an index I. So then for every particle you will have a mass mi, a diameter di, a position xi, a velocity vi, but we'll also have an angular velocity omega I. So omega I is a vector which points along the axis of rotation, and the magnitude is equal to the angular velocity. And then of course we'll have the moment of inertia. So just in case I went a bit fast, so we just write down this: mass, diameter, position, velocity, angular velocity, and then moment of inertia. So these are properties of the particle. And what we would like to know is, we'd like to know what is xi, vi, and omega I. How do they change with time? Right? So you're given all the initial positions, and what we need to do is obtain xi as a function of time, vi as a function of time, and omega I as a function of time. And so what is the governing equation for this? As I was saying, that this equation very well. So the governing equation is just mi into dvi by dt, that is mass into the acceleration, the rate of change of velocity with time is acceleration, is just equal to the sum of all forces acting on the particle. So Fijr is the force applied by, or the J forces that are acting on particle I, and these will be the interparticle forces, that is the force exerted by particle J on particle I. And then you have the force due to gravity, which is just mi times G. So Fij is the force applied by particle J. Of course, we are talking only about particle I. We are looking at one particle I. Okay, and there may be other four particles around it which are exerting forces. And so let's say there are J such particles that are applying forces on it. So Fij is the force applied by particle J, obviously on particle I. and G is just gravity. So these are the only forces that we have to worry about. And so we need to solve this equation. And for one particle, this is very easy to do. But for many particles, because this is not just one equation, you have for every particle this equation. So I will actually go 1, 2, 3, right up to the number of particles we have, which is n. So if you want to solve for only one particle, we have already done that bouncing ball problem. It's easy to do. But when you have a very large number of particles all interacting with each other, this can't be done analytically. So you have to have numerical methods to solve this. And so what are the numerical methods? So two approaches are used. For this. One is called the hard particle, or event-driven method, and two is the soft particle or discrete element method. It is also called DEM. And I'm going to tell you a little bit about both of these. And the basic idea is that in the first one, it's a hard particle. That means it's actually infinitely hard particle. You assume that the collisions are instantaneous, and so you solve from collision to collision. And then the second one, you assume that the particles are deformable. So like how we did the problem for this Hertz sort of deformation, we can do the same thing and take into account the deformation of every particle. So collisions have a finite time. So let's start with the hard particle method. These are the numerical methods. So let's look first at the hard particle method in some detail. And how does this method work? So the idea over here is that since collisions are instantaneous, what this implies is that at any time, no more than one collision can occur. So this implies zero duration of a collision, and what this means is that at most, if you look at any time, there will be either no collision or at most one pair of colliding particles at any given time. And when there are no collisions, there is no interparticle force. So if two particles are not colliding, so what we say is between collisions, force is zero. So we can easily integrate.
Hello, sir.
Ah,
Hello, sir. Can you please explain that term, that zero duration term?
why is a collision? No, that's the assumption, no, that if you say that the collision is instantaneous, that the time of collision is zero, so you will understand why now that as we go through the derivation, you'll understand why two collisions can't happen at the same time. Because there always be a very tiny but finite difference between them. The difference may be 10 raised to the minus 20 seconds, but there will always be some difference between the time of collision between any two pairs. You will never have exactly the same time. Because if you go to more decimal places, you'll be able to see the difference in time. And so, but when two particles are not colliding, there is no force acting between them. And only when they collide, there is a force. So Fij is zero between collisions. And so this means that governing equations become simpler and we can easily integrate them. Because now each equation is independent of all the others. So now you only have this. And if you want to find out what is the position of the particle, then we simply write down dxi by dt. The rate of change of position is just given by vi. I didn't write it down earlier, but this is true even when force is not equal to zero. So these are the equations for each particle, but each can be solved independently now. So between collisions, the particles just move independent of all the other particles, and that can be solved. So the basic procedure that we follow in this method is that first step is compute the time at which the next collision occurs. So, all the particles are moving. So now we have to look at every pair of particles and see what is the time of collision for those two particles. And we can easily calculate that since we already know what is the way that they're moving. And once you do this, since we know which is the minimum time, that will be the time for when the next collision occurs, then move all particles. Let's call this time as Tc. Then we move all the particles for Tc. They'll all move independently. And then update the velocities of the colliding pair. Okay, this is it. And then you go back. So just to sort of illustrate this, let's say we have all these particles moving. So here, let's say this has a velocity here, this has a velocity here, and this has a velocity here. Now what will happen is, if we move the time forward, this particle will move in this direction, this particle will move in this direction, and this particle will move in this direction, and they'll all move independently of each other because there's no force acting between them. But at some point, essentially, this particle will collide with this one. So you will have actually this particle over here and this particle over here, and so after time tc, these two particles will be colliding. And then of course by then this particle would have moved over here. So what we do is we calculate what is Tc, which is the time at which the first collision will take place, then move all the particles by the time Tc to these positions. And now since these particles have collided, they will have new velocities. They will no longer be moving in the direction of the arrows shown, but they will move in some new direction. So we have to calculate the new velocities. So this is what is the procedure. Okay. So now let's look at how do we implement this. So this may give you a better understanding. So the first thing I'd like to do is make everything dimensionless. This is always a convenient thing to do. So let's suppose the particle diameter is d. So then let's make all distances dimensionless. So the dimensionless variable is x bar. Let's make that x divided by d. Okay. Then let's define t, dimensionless time, to be the time divided by a characteristic time that is dependent on d and g, where g is the acceleration due to gravity. So if you do d divided by g, then that will give you units of seconds squared, and then square root will give you of seconds. So this is a dimensionless time. Similarly, I can define a dimensionless velocity as the actual velocity divided by a velocity constructed by g and d. We know g times d is units of velocity squared. So we take square root and that will be that. Then supposing our box dimension is L, then the dimensionless box dimension is just L divided by D. We take the mass to be just 1. That is, the characteristic mass is equal to mass of a particle, that is m. The characteristic distance is diameter, so the dimensionless diameter is obviously 1. And then the dimensionless gravitational vector is equal to the gravitational vector divided by the magnitude. So that is nothing but the unit vector in the direction of gravity. So by doing this, making things dimensionless, the equations become a lot simpler. And the equation can be written now as just dxi. I'm sorry. You don't have any mass or anything like that, diameter coming in. So dvi bar by dt bar is equal to g hat, and then dxi bar by dt bar is equal to vi bar. So in dimensionless variables, this is what the two equations are. So this is saying that the mass into acceleration is equal to the sum of the forces acting, and then the only force acting when there is no collision going on is gravity. So that's the only force G. And the rate of change of position is equal to the velocity of the particle. So this is the governing equation. So now how do we do the first step? Calculation of collision times. How do we do this? Well, we can easily, integrate these two equations. And if we integrate them, and you would have done this before in school also, what it says is a particle moving in under gravity. There it's just that xi at any given time is equal to the position at time equal to 0. So you've seen this, x is equal to ut, x is equal to x0 plus ut plus half at squared. So that's what it is. The acceleration is just g hat and delta t squared. So this is the displacement of a particle for time t, where xi prime is the new position and xi is the. So here, though these variables are dimensionless, I'm just saying over bars have been dropped because it's no point writing it. We know everything is dimensionless. So now on, I'll not write over bars. You can just assume that it's dimensionless. So now if we know this, then what is the condition for collision? Between any two particles. So let's call them I and J. So xi prime is the position after some time delta t, given that the position initially is xi. So we are given xi, vi and g, and for any given delta t we can find out the new position xi prime. And so what is the position, what is the condition for collision? So if we look at particle I, and let's say this is particle J, they're at the point of collision, okay? And so the position over here of the center, this position is xi prime, and this position is xj prime. So supposing these two particles have collided, what does that mean? That means that the center to center distance, this distance is just equal to the diameter of the particles. Say they are all equal size. So then this is just the diameter of the particles. The distance to center at the point of collision is just d bar. And in our case, we have taken everything dimensionless. So this is just 1. So when the center to center distance becomes equal to 1, then we say that the particles have collided. And if we want to write it in vector form, then what we say is xi minus xj prime must be equal to 1. So this magnitude means that's the length of the vector xi prime minus y xj prime. But we already have a formula for calculating xi prime and xj prime. So if we look at this, if we substitute for xi prime and xj prime, then what this tells us is that the magnitude of, now I put it in terms of xi and vi, what you see is this is nothing but magnitude of xi minus xj plus vi minus vj delta t is equal to 1. Well, what happened to the third term? Since it's the same for both the particles, it simply cancels out. So this is, you only get two terms over here. Now you know that by definition of the magnitude, this is nothing but square root of v dot v. So the magnitude of any vector is just this. So magnitude of v squared is just equal to v dot v. So let's apply the same formula. Well, I don't mean v, so let's call it by some other variable. Let's call it as u, just so that there's no confusion. So u is any vector. So we can do it for this vector also between the magnitude signs. So basically what it says is that xi minus xj plus vi minus vj times delta t dotted with itself is equal to, so this is this vector squared, so this must be equal to 1 squared, which is still equal to 1. Now if we take, now this is goes back to what we were looking at just a little while ago. So what we'll see is that if we take the dot product of this, so then this is nothing but xi minus xj dotted with xi minus xj. So this is the magnitude of the distance between the two particles at any given, this is remember, this is the initial positions. The position after delta t is equal to 1, but the initial position, that could be anything. You know, they were far away, now they are colliding after a certain time. So this is not equal to 1. So this is the dot product between this and this. Then we can have one other dot product between this, the velocity terms, plus vi minus vj dotted with vi minus vj times delta t whole squared. So that's the second term. And then you'll have two terms, xi times vj, and this is again vj times xi. Now taking the order of dot products doesn't matter. So this will give us 2 times xi minus xj dotted with vi minus vj times delta t is equal to 1. So you can see that this quantity xi minus xj dotted with xi with itself, this is just the magnitude of the initial distance squared. This is a scalar quantity. This quantity is again the magnitude of the difference in velocities whole squared, scalar quantity. And this is the projection of the relative velocity on the line joining the two particles. And that is also a scalar quantity. So if you look at this equation, this is nothing but a quadratic equation of the form a into delta t squared plus 2b. Not write it as 2b, just write it as b times delta t plus c is equal to 0. What is a? A is nothing but vi minus vj dotted with vi minus vj. Well, this is the magnitude of the relative velocity. This is always greater than or equal to 0. So that is given to you. Then if you look at c, then this is equal to the magnitude of the initial separation between the two particles, xi minus xj, minus 1, because you take 1 on the other side, so you have minus 1. And we don't know, this may be greater than 0 or not. And the third condition, and this b is just equal to 2 times xi minus xj dotted with vi minus vj. Okay. I'm sorry. This distance also is greater than equal to 0. I'm sorry. C is also greater than equal to 0. Why is that? Well, the simple reason is that the closest distance between them, between x, the two particles cannot penetrate each other. So the smallest distance between xi and xj can be the diameter, which is 1. So since this can be at the most, the lowest value this can take is 1. If you do this minus 1, it has to be greater than or equal to 0, since xi minus xj magnitude is always greater than or equal to 1. So here we have it. So A is this, and now we can write down what is the time for these two particles to collide. So this is equal to minus b plus or minus square root of b squared minus 4ac raised to the power of half divided by 2a. Now we have seen this is greater than equal to 0. This is also greater than equal to 0. So if you look under the square root sign, uh, the right hand, this term 4ac is always going to be negative. So your b must be large enough. So you must have b squared must be greater than 4ac for a collision to occur. If this is not satisfied, then the two particles will never collide, no matter what the time. A second condition for collision to occur is that particles should be moving towards each other. So if the particles are moving towards each other, then what it should mean is that, let's say for example, if we look at these two particles, or let's just look at any two particles here and here, and this distance, let's call this as I and this is j. So then this vector is nothing but xi minus xj. So that is a vector joining the two centers. And so if the two particles have to be moving together, then we can write down a velocity vector that is vi minus vj, like this. So this is like assuming that the coordinate system is centered on j. So this velocity is 0 and this velocity is vi minus vj. So this will be the velocity vector vi minus vj over here. And if the two particles are moving together, so if the velocity vector is pointing in some other direction, then the distance between the particles will increase. If you want the distance between the particles to decrease, then which is another way of saying we want particles to move towards each other, then the condition is that the dot product xi minus xj dotted with vi minus vj, this should be less than 0. So that means this implies that b must be negative. If b is positive, then that means that your velocity vector is pointing like this. And you know that when you take the dot product, you are essentially taking the projection of this vector here. So the component of this vector in the direction along the line joining the centers is like this for this velocity vector. And if you look at this one, it is like this. So if the velocity vector is, if the dot product is positive, that is the red case, the particles are moving apart. If the dot product is negative, like the blue vector, then the particles will move together. So there are two conditions that are required for a collision to occur, and one of them is that b squared must be greater than 4ac, otherwise your collision time will be imaginary, and the second is that b should be less than 0, otherwise you will get a negative collision time. So by doing this, we can easily find out whether or not a collision will occur. And so the way that we do it is we can calculate delta t for every pair of particles and find delta t minimum. Okay, and then once you know delta t minimum, then all we have to do is we apply this formula to find out the new positions. Okay, so when we do the next step, is step 2 is to move all particles until the next collision. So then you just put the new positions of the particles are xi prime is equal to xi plus vi delta t min plus half g hat delta t min squared. So now you look at all the particles and you say, okay, these two particles are going to collide and they will collide in time delta t min. Then you move all the particles by a time delta t min. What will happen is that the two particles that are colliding, they will just touch. And then the next thing that you do is, all you do is change the velocities of the colliding particles. So this is what you have to keep repeating over and over again. And this we have seen already. We did some simple calculations to show that what are the velocities after a collision when the coefficient of restitution is epsilon. So then this can be simply written as so these are the two particles I and J which are colliding. So only their velocity is affected by the collision. All the other particles remain the same. And if you see this, here n is the unit normal vector in the direction of the line joining the centers. I should write this as xi prime, xj prime. So this is after the particles have moved. So these are the new positions. And then Vi is of course the original velocity. So Vn is equal to Vi minus Vj dotted with n, the unit normal vector. That is the component of the relative velocity along the line joining the centers at the point of collision. And in the same way, we can do more. So if I just go back, we had two methods, hard particle, soft particle. In today's class, I only talked about the hard particle method. And there the idea is that all particles keep moving until there is a collision. Then those two colliding particles, they'll start moving apart. And then another pair of particles will collide and so forth. And so what we have to do is we have to find out which are the pair that will collide first. And then to do that, we use the condition that the distance between the centers at the point of collision is equal to 1. We get a quadratic equation for that. And we also get a condition that for a collision of between two particles to occur, you must have this and this satisfied. So we find out the delta t for every pair of colliding particles and then find out what is the minimum value. And then once we have this, then we move all particles by this minimum time. So then all the particles will move and only the colliding particles, they will take up this configuration. They'll be touching. And then at that point, you update the velocities of those particles and by using these formulas. So you'll have new velocities for I and j. The velocities of everything else will be the same. Okay. So, this is a really simple algorithm. And so what I want to show you is excuse me. I think I can stop this. So now what I would like to show you is that it's really easy to even write a short program to do this. And here is so this is our program. Okay, so this program is written in C language, and I hope all of you know this language. So if you look at this program, it's sort of a general one, but it first finds it opens the parameter value file, which reads the number of particles, the size of the box, the coefficient of restitution, and the velocity. And then it reads once we know number of particles, then it reads the positions and the velocities of every particle and their radius. And of course, it writes those positions down just so that we note what were the initial positions. Then there is a function that you check collisions between the particles. You check collisions with the walls because the particle could collide against the wall also, and it's quite easy to find those collisions because if they're moving in a certain direction, you just find the time that it takes to reach the wall. And then once you do this, then it will print out the values of the particle pair that is colliding, I min, J min, and DT min. And then what is the possibility that the particle collides with the wall? So what particle collides with the wall and what is the time for collision with the wall? And then it writes down the positions. So if the particle collision is less than that, then you update the velocity of those particles and then you print out their positions. Otherwise, you do the collision with the wall. So this is the overall scheme. And here is the way that we find out how do we check for collisions. Well, we go for I going from 1 to the number of particles. This is a do loop. Then there's another do loop which goes from I plus 1 to, because you already, you have to check I versus J, but J, you don't need to check it twice. So if you don't want to check everything twice, then if it is I, then this is I plus 1 to n parts is the second do loop. And then the time for collision is given by this Fn dt. This is a function which calculates the collision time between particles I and J. And if this newly calculated time is less than the minimum time, then that is called the minimum time, and then I min is equal to I, J min is equal to J, and so forth. And what is this function dt? Well, you calculate the difference, the components of the xi minus xj, then you calculate A, you calculate B, and you calculate C. This is B, of course, is twice B, C is equal to C minus 1. Then you find out this, calculate this B squared minus 4AC. So, and then you check if determinant is this quantity is greater than 0, and if B is less than 0, only then calculate what is dt. Otherwise, it will keep a very large value of the time. Dt initialize at e raised to 10 raised to the power of 10. So, it's a huge value. So it will return this value if there is no collision, but if there is a collision, then it will give you a value of dt. So this is this program. And then, what I did initially was to just have one pair of particles. So it simply writes down the position of two particles, and those two particles will collide. So, oh no, it writes down many particles, but only two collide, I think. Okay, so let's see how this thing runs. I'm going to put all these programs up there for you to play around with. So this is just the first collision. Okay, and so I'm going to run this and then stop. So there's this small script. What it does, it removes all the data files. It compiles the initialization program. It compiles this program box, and then it runs box, and then it plots the positions. So this is called run one. So it'll just give you the first collision. So this is what is the thing, that initially I started with the positions. The orange particles The orange circles show the initial positions of all the particles. So there are 25 particles here, you can see, and all of them have been given random velocities. Okay. And then when we do this, we see that particle 18 and 19 will collide, and the time for the collision is 0.86 seconds, or 0.86 dimensionless units. And here are the two particles. These two particles, you can see they are moving in this direction and this direction. So these are the two particles that will collide, and after they collide, the velocities will change to this. You can see the gray arrows are the initial velocities, the black arrows are later velocities, and this is after 0.86, after time of 0.86. This is where these two particles will be. So if we look at now what are the positions actually of the particle, all the particles will of course move. So the first step is calculating this. This is what we have calculated. Now let's move all the particles. And so these are now the blue, orange are the initial positions, and blue is the position after time 0.86. So you can see this particle has gone there, this particle has gone there, this has gone there, here. In this simulation, I'm taking gravity to be equal to 0. So there is no gravity in the system. So that is a little bit of a simplification, but it's not much. There are many other examples where, there are example programs in which there is gravity, which I'll show you later. So this is how you can see every particle moves in the right way. And that's it. So with that, I'd like to end. And if you get a chance, please try out this. And we'll do more example problems regarding